Hello and welcome. Let me begin the content of this session. In the previous session, we reached to the convergence theorem. We see some of this theorem. For example, for simple functions or non-negative functions, okay? But this is more general version of dominated convergence theorem. Suppose X mu is a measure space G from X to 0 infinity is S measurable function, and the integral of G with respect to mu is finite, so that G is mu integrable, okay? Then for every created now, there exists one delta positive such that the integral of G with respect mu on B is strictly less than epsilon for every set B belonging to S such that mu of B is less than delta, okay? Elementary theorem or proposition that we need for dominated convergence theorem, okay? This is not dominated convergence theorem, but this proposition is useful if G is mu integrable. Then for each epsilon there exists one delta such that for each B in S, by this property we have this inequality, okay? And its proof is easy because for each epsilon, positive epsilon, this is a simple S measurable function such as H, such that H is between 0 and G, and this subtraction is less than epsilon divided by 2. And the existence of this function H follows from proposition 3.9. You can see this because H equal to the maximum of this set H of X such that X belongs to X. This is a number, okay? The maximum of these real numbers, and that delta is a strictly positive real number such that H multiplied by delta less than epsilon divided by 2, okay? We can choose delta sufficiently small such that this inequality is held. Now suppose B is an element in S with this property, then we have the integral of g on b equal to integral of g minus h plus integral of h on b. In fact, the integral of h on b was added and omitted. Okay, added and omitted, and this is less than or equal this integral h mu of b, because this function h is less than or equal this real number h. Okay, so that this is less than or equal the integral of capital H d mu, and capital H d mu, the integral of capital H d mu equal to this. Okay, in fact, let me active my board. Okay, I think its battery have problems, so that we cannot write this for you. Okay, okay, let me a minute again. Okay, but this is very easy, because this integral is less than or equal the integral of capital H. Okay, this H, and the integral of capital H on b equal to this h mu of b, and mu of b is less than delta, so that this is less than h delta, and this is less than epsilon divided by 2 by this inequality, and h delta is less than epsilon divided by 2, so that whole of this is less than epsilon, and we prove our inequality for any b such that mu of b is less than delta. Okay, we prove this inequality for any b with this property, so that this proposition was proved, and its proof is easy. Then we have this proposition: suppose X S mu is a measure space, G from X to 0 infinity is S measurable, and the integral of G d mu is finite. Then for every positive epsilon, there exists an element of S such as E, such that mu of E is finite, and this integral is less than epsilon. Okay, and this is very nice proposition that is a generalization of Egorov theorem for finite measure spaces. Okay, X S mu is measure space, not necessarily finite, and G from X to 0 infinity is S measurable and mu integrable. Then for every epsilon, there exists an element of S such that mu of E is finite, and we have the integral of g on x minus e is less than epsilon. Okay? Dear students, do you have my voice and do you see image? Hello, Sajjad, Muhammad, Leila, and do you have my voice? Do you have my voice and do you see my image? Can you see slides and do you have my voice? Let me write for you. Sajjad, Muhammad, okay. For this proposition, we can see that for every epsilon, there exists an S-partition of x such as P equal to A1, A2 up to the AM, such that the integral of G d mu is less than epsilon plus L of G and P. Okay? This is by the definition of Lebesgue integral, because this integral is the supremum of this Lebesgue lower sums, okay? By the property of supremum. This is supremum of these numbers, okay? So that for each epsilon there exists one element such as this, such that we have this inequality. Now let it be the union of those Rj such that the infimum of f on Rj is positive, so that if f equal to 0 on Rj, this Rj not in this union, not belong in this union, okay? E be the union of those Rj such that this infimum is positive, not equal 0, okay? Well, then mu of E is finite, because otherwise we would have this lower Lebesgue sum equal to infinity, okay? Let's see the definition of L of G and P, which contradicts the hypothesis that this integral is finite. Because if this is equal to infinity, because if one of these elements equal to infinity, its supremum is infinite too. And the supremum of this L equal to this integral, okay? If one of this equal to infinity, this integral must be equal to infinity, but we assume that this integral is finite, okay? Now we see that the integral of g on x minus e equal to this. I cannot write for you. I'm very sorry for these problems. Okay. It have some problem, but if I can write by my fingers, the integral of g c of x minus e d mu equal to the integral of g multiplied by c of x minus c of e d mu, okay? And this is equal to the integral of g chi of x equal to 1, okay? d mu minus the integral of g chi e, okay? Chi of e. G multiplied by this is equal to 1, constant function, okay? So that we have this, and this integral is less than epsilon plus L of g and p, and this is less than L of chi of e, g and p, because this integral is the supremum of such as this element, and we have this inequality, and these two are equal, so that we see that this combination equal to epsilon. so that we have the integral of g on x minus e is less than epsilon. Okay, where the second line follows from 3.30 and the definition of the integral of non-negative function, and the last line holds because infimum of f equal to 0 on Rj for each Rj not contained in E. Okay, it is clear. Now suppose X is mu is a major space and this is a sequence of S measurable functions on X such that the limit of a k of X k tend to infinity equal to f of X for every or almost everywhere X. Okay, every or almost everywhere. Please note that if we write, for example, fk tend to f this equal to limit of fk k tend to the infinity equal to f, or equivalently this means that for each x belong to x, the limit of fk of x k tend to infinity equal to, f of x for this we can write this fk tend to f pointwise. Okay, pointwise, pointwise. pointwise. Okay. But if we write FK tend to F almost everywhere, this means that or mu almost everywhere. Okay, the mu of the set of all x in x in x such that this limit is whole. The limit of FK okay of x not equal to f of x f of x okay, the measure of this set equal to 0. K tend to infinity. Okay, please note that if FK tend to F pointwise, for each x we have this equality, and if FK tend to F almost everywhere, the measure of this set must be equal to 0. This set in this case equal to empty set, okay, because for each x we have this equality and we don't have this equation, okay, so that this set in this case equal to empty set and the measure of empty set equal to 0, so that if FK tend to F pointwise, then FK tend to F almost everywhere too, okay, and we can assume that FK tend to F pointwise or almost everywhere, okay. In any case, if FK tend to F pointwise or tend to F almost everywhere, this equality is not hold necessarily, and we see theorems such as monotone convergence theorem and dominated convergence theorem that this equality is hold. This equality is not hold in general, okay. We already have two good theorems about interchanging limit and integrals, because this f is the limit of FK, okay. Specifically, the monotone convergence theorem requires all the function to be non-negative and it requires the sequence of functions to be increasing. The bounded convergence theorem 3.26 requires the measure of the whole space to be finite and it requires the sequence of functions to be uniformly bounded by a constant. Okay. The next theorem is the grand result in this area for this interchanging. Okay, and it's very important. Dominated convergence theorem. Suppose X is mu is a measure space f from X to extended real lines is measurable and f1, f2 up to the end are s measurable functions from X to this interval such that we have this limit or fk tend to f pointwise. Okay, for fk tend to f for almost everywhere, so that we have this case. Okay, the measure of the set X such that we don't have this equality equal to 0. Okay. If there exists an s measurable function g from x to 0 infinity such that the integral of g d mu is finite, and for every natural number k and almost everywhere x in X we have this inequality almost everywhere, so that the set of all x in X such that this equality is not whole have zero measure. Okay, then we can replace limit and integral. The limit of integral of fk equal to the integral of limit of fk, because this f is the limit of the sequence fk. Okay, so that we can interchange limit and integral by these assumptions. And this is dominated convergence theorem. This is very important theorem, and its proof is easy, because if we suppose g from x to 0 infinity satisfies the hypothesis of this theorem, and suppose E is an element of S, then the integral of fk minus the integral of f with respect to mu equal to this, because this integral equal to the integral of fk on E plus the integral of fk on x minus E, and so similarly this integral equal to the integral of f on E plus the integral of f on x minus E, so that we can write this subtraction by this, and this is less than or equal this by triangle inequality. This absolute value of this and absolute value of this. Okay, and both of this is less than this integral by this assumption. Okay, because f car is less than g, and so that f is less than g, so that the integral of f car and the integral of f is less than the integral of g on this set. Okay, now we can consider two cases. Case 1, if mu of x is finite, then for every epsilon by this proposition 3.28 there exists one delta positive real number such that the integral of g on b is less than epsilon divided by 4, and we see this proposition for every set b such that mu of p is less than delta. Now by Egorov's theorem, because mu of x is finite and Egorov valid in finite measure spaces. Okay, by Egorov's theorem there exists a set E in S such that mu of its complement is less than delta strictly, and the sequence converges uniformly to f on E. Please see the Egorov theorem for this result. Now by this proposition 3.32 and 3.33 we have the integral of fk minus the integral of f is less than epsilon divided by 2 plus this integral. Now because this sequence converges uniformly to f on E and mu of E is finite, the last term on the right is less than epsilon divided by 2. This for all sufficiently large cars, thus this subtraction is less than epsilon, and so that this integral tends to this integral. The limit of integral of fk equal to the integral of f with respect to mu. So that in this case our proof is complete. In the case of mu of x is finite, we prove this equality. But if mu of x is not finite, mu of x equal to infinity, for every epsilon greater than 0, by the proposition 3.29 there exists an element of S such as E such that mu of E is finite, and we have this. Okay, we see these two. The inequality above and this proposition implies that the integral of fk minus integral of a is less than epsilon divided by 2 plus this subtraction. Okay, integral of fk on E minus integral of E and integral of f on E. Okay, now because we can divided both of these to integral of e plus integral of x minus e, similar to this, okay? But both of these is less than epsilon divided by 4, okay? So that this is less than epsilon divided by 2. 2 epsilon divided by 4, okay, is equal to epsilon divided by 2. So that you can, a method similar to this paragraph, we see that this is less than epsilon divided by 2 plus this, okay? This 2 is less than epsilon divided by 2 because this is less than epsilon divided by 4, okay? And so that by the case 1 as applied to the sequence, there is restriction of this sequence to E. F1 restricted by E, F2 restricted by E up to the end. The last term on the right is less than epsilon divided by 2 because this tend to this integral by the first case, okay? So that we can consider this less than epsilon divided by 2 and all of this is less than epsilon, so that this integral tend to this integral, okay? And we have this important theorem, dominated convergence theorem. And we have an important relation between Riemann integral and Lebesgue integral. At first, please note that a function is Riemann integrable in and only if and only if this function is continuous almost everywhere, okay? F is continuous almost everywhere. Please note that. For example, if you consider F from A and B, to R real numbers, okay? If we say that this F is continuous, continuous continuous almost everywhere almost everywhere. Okay, not continuous, continuous almost everywhere. So that we have these propositions. Is equal to the measure of mu of this set, the set of all x in A and B. A and B. A and B such that F is not continuous. F is, sorry, I have a problem for this board today, is not continuous at x the measure of this set equal to 0. Okay, the measure of, and we can consider this measure lambda because we have Lebesgue measure. Okay, we have Lebesgue measure, sorry, we have Lebesgue measure in subsets of real line. Okay, we can consider lambda as measure. This equal to 0, and so F is continuous almost everywhere whenever we have this condition. The measure of the set all x in A and B such that if it is not continuous equal to 0. Okay, now if f is bounded function, then f is Riemann integrable if and only if this measure equal to 0 or f is continuous almost everywhere. The set of all x that f is not continuous have 0 measure. Okay, if and only if, this is very important. Furthermore, if f is Riemann integrable and lambda denotes Lebesgue measure on R real numbers, then f is Lebesgue measurable and the integral of f Riemann integral equal to Lebesgue integral of f on A and B. The integral of Lebesgue equal to the integral of Lebesgue. Okay? If f is Riemann integrable, then f is Lebesgue integrable. We must write integrable, not measurable, okay? F is Lebesgue integrable and these two integrals are equal. Okay. Similar to previous semester, I can choose some practices and you answer to these questions that we consider a part of your exam, a score of your exam by this solving and exercises, okay? Let me write this for you. Okay, please read.
خلال الفصل الدراسي الماضي سأحدد لك تمارين لحلها وسأحدد جزءا من درجة الامتحان باستخدام هذه التمارين. خلال الفصل الدراسي الماضي سأحدد لك تمارين لحلها وسأحدد جزءا من درجة الامتحان باستخدام هذه التمارين.
Okay, do you understand? Okay, one of these practices is this theorem. Please note that I want that you read the proof of this theorem. This is not difficult. This is straightforward, I think. But you must use the definition exactly. Okay?
أحد هذه التمارين التي كتبتها هو الدليل على هذه القضية. أحد هذه التمارين هو كتابة الدليل الدقيق لهذه النظرية.
Okay, so that I want that you read the proof of this proposition and then write it for me accurately and by details. Okay, let me write again.
قراءة دليل هذه النظرية بالكامل ثم إرساله إلي بدقة وتفصيل. قراءة دليل هذه النظرية بالكامل ثم إرساله إلي بدقة وتفصيل.
Okay, do you understand? Do you understand? It is clear for you? Okay, thank you. So that you must read the proof of this theorem exactly and write it for me by complete details. Okay, by complete details. And we have this definition of integral of f on a and b, but a and b can be considered infinity, minus infinity, or b can be considered infinity. If f from this interval is Lebesgue measurable, then the integral of f on this interval means integral of f with respect to lambda on this interval. This interval may be minus infinity up to the infinity, okay? When lambda is Lebesgue measure on R, and the integral of b to a is defined to be minus the integral of a to b, okay? This is the definition. And so that we have this equality for each a, b, and c by this definition, okay? Okay, let me continue the next definitions and contents in the next session. Do you have any questions, dear students? Do you have any questions? Okay, thank you very much. Thank you for your attention and goodbye for now.